guys, and welcome to a new video. In this video we are going to solve some exercises on electric forces and electric field. The electric field. So in the first exercise we have two charges. The first charge, let's call it Q1, and then we have here the second charge Q2. So the two charges are located at a certain distance, and we know that here in this point P, the electric field, the total electric field is 0. We know that the distance between P and Q2 is D, and this distance is due to D between Q1 and P. We know that the charge Q2 is 3 times 10 to the minus 5 coulomb, and we have to find the charge here, so the charge of the first charge. We have to consider the fact that the total electric field here is 0. The electric field here is given by the electric field of the two charges. So the charge Q2 generates a electric field which we can call E2, which is given by the constant K times the charge over the distance, so D squared. So we already know Q2, we know that the distance is D, but we don't know the charge here. But we know that similarly the charge, the first charge here, will generate an electric field here given by, so we can call it E1, given by K, the constant, the charge Q1 over the distance squared. So the distance here in this case is 2D, so squared will be 4D squared. So we know that here the electric field, the total electric field is 0. So it means that these two electric fields have to be identical, because here we have to sum these two electric field, but if the sum is 0, it means that E1 is equal to E2. So if E1 is equal to E2, it means that K Q1 over 4D squared is equal to K Q2 over D squared. Let's notice that Q1 and Q2 have to be of the same sign. So if Q2 is positive, Q1 has to be positive. So in fact here, if Q2 generates an electric field of this kind, Q1 has to generate an electric field of this kind, so with an opposite direction. So here we can cancel K and D squared. So at this point we can get that Q1 is 4 times Q2. So in this case would be 12 times 10 to the minus is a superposition principle that holds when it comes to the electric field, basically. In the second exercise, we have again two charges, and these two charges are hanging from by two different strings, which are the same, which are identical as well. And we know that these two strings form two angles which are identical, theta and theta. So we have that the charge of the two charges here is q, so the same for both, and it is 8 times 10 10 to the 5 coulomb, and we have that L is 1.5 meters, and we know the distance at equilibrium between these two charges, which is d, and the distance at equilibrium is 4 centimeters. So this is the situation of this exercise. These two charges are at equilibrium, and we have to find the angle theta and also the string force given by the string here and here. Okay, so the situation here is symmetrical, so the two charges are subjected to the same forces, and theta can be found easily, given that we know the length of the string, and we also know the distance between the two charges. So we know that here we have a triangle, and this angle is 90 degrees. So given that we know that the sine, we can write that the sine of theta is given by d over 2, so d half over L. So from here basically we can find theta, because theta will be given by the inverse function of sine of d over 2L. So if you put the values of d and L here, you can find easily the value of theta. So here basically theta is given by the geometrical conditions of the problem, of the situation. And now we have also to find t, so the string force, the force given by the strings, and this force can be found given that we know that the two charges are at equilibrium. So that means that the sum of the forces is 0 for both charges. Actually, we can focus just on one of the two charges, because here, as we said, the forces are the same, and the situation, the system is symmetrical with respect to the vertical axis here. So here basically we know that the charge here on the left, for example, is subjected to the weight of the charge, obviously, and we have the string force here acting along the string, and then we have the electric force here, which is pushing this charge to the left, because because the two charges here have the same charge, so since they have the same charge, the force is pushing the two charges away from each other basically. So we know that these three forces, the sum of these three forces is 0, but we have to focus on the two directions, y and x, for example. So we know, for example, that as far as the x-axis is concerned, so the horizontal direction, we have the component of the string force, so the component of this force that we can call, for example, if t is the string force, we can call its component along the x-axis tx. So tx, and then we have minus this electric force, which we can call phi e, and this is equal to 0. So okay, so we know that tx would be given by t times the cosine of this angle, but the cosine of this angle is equal to the sine of theta. So we can write that tx is given by t times the sine of theta. And okay, and as far as phi is concerned, we know that phi is given by the constant k, the charge squared, q squared, over the distance d squared, the distance between the two charges. Okay, so at this point we can write that d times sine of theta squared, and basically here we know everything except for t. So here basically we can write that t is given by k q squared over d squared, and then we have 1 over sine of theta. So let me maybe write it here more clearly. K q squared, and then we have d squared sine of theta. Okay, so this is the force given by the string basically. We also know that as far as the y-axis is concerned, we know that here also the sum of the forces is 0, so we can write that dy minus the weight of the charge, so this one, this force, which is given by m times g. So this sum, we know that this difference is 0. So from here we can also find m, the mass of the charges, and we can, since tx is given by t times sine of theta, we can write that dy is given by t times cosine of theta. So at this point we have t cosine of theta minus mg equal to 0, and from here we can write that m is given by t cosine of theta over g, but we know that t is this one, so we can write that m is given by k q squared, and then we have d squared g, and then since we have here sine of theta and here cosine of theta, here we would get the tangent of theta. Okay, So here basically we found both m, the mass, and the tension, the string force, the force given by the string.